So those were kind of some of the things that we talked about yesterday. And then one other thing we did with number 19, we did, and you did number 21. So we'll go through number 21 together just to make sure. Because the problem like 21 is one of those basic calculus problems that by the end of the year you're going to have done many times. And you're guaranteed to see on the AP exam and have to go through with the number line and stuff like that. I mean, it is one of those, at the end of calculus in May, if you had to write down a list of like the 5 types of problems that you run into the most or you've seen over and over again, that will be one. A problem like number 21. Okay, so it's definitely one you want to get down and understood. Okay, all right. So there was my discussion on that. Okay, let's go to your book assignment on 3 through 12. Again, I apologize for some of you who think this is too easy. But again, it's just a fundamental concept here. So now that we've said that big F, this is the little f graph. So we got big F. So we got big F stationary point 0. We got increasing, decreasing, concave up, concave down. So we got plus, minus, increasing, decreasing, right? Like that. So this row here would be big F prime right here, right? So let's move through this pretty quick. So it says, what's the slope of big F at 4? Well, isn't that like asking this? Well, what's that another way of saying? That's little f of 4, right? Same thing. Well, little f of 4 just means come over here and read it, and what's that y value? 5. Bingo. Where is big F increasing? Big F's increasing when little f is positive. This is little f. When is this positive? All the time, 0 to 10. It's always above the x-axis. Little f's always above the x-axis, 0 to 10. Where does big F have points of inflection? Big F's going to have points of inflection when it switches concavity. When big F switches concavity, little f has to switch up to down, down to up. Where does that happen? There and there. Remember when F prime had maxes and mins, that's when F had points of inflection. Well, that's what we're doing right now. This is our F prime row. Right now it's big F prime. So when big F prime has maxes and mins, big F's going to have points of inflection. Okay, same things we did before. Where is big F concave down? That's when little f is decreasing. So that's from here to here, 1.14 to 8.19, right? What is the value of big F double prime of 5? Well, big F double prime of 5 is the same as little f prime of 5. Big F double prime of 5 is going to be the same as little f prime of 5. Well, this is little f, so little f prime would be the slope. So drawing a tangent line right here and do a slope. What do you got, negative 1.5 or something? Somewhere in that ballpark, okay? Why does f double prime have its minimum value at 4.67? Well, remember, a minimum value is either, if they're all positive, it'd be the littlest positive, or if they're positive and negative, the littlest value would be the one that's the most negative, right? Well, so big F double prime is little f prime, which are these slopes. So these slopes are some are positive, some are negative. So the minimum value would be the one that's the most negative. Oh, yeah, well, it gets negative and more negative until right there, then it's less negative. Right there, it's the most negative slope at the inflection point. So that could be your explanation. What's the equation of L? In the directions, they say L is the tangent line to big F at 0. So we need big F at 0, and we need big F prime at 0, right? We need the point and the slope. Well, big F of 0, they told us, was 10. Big F prime is the same as little f, right? Big F prime is the same as little f. And what's little f at 0? 7. So now we got our point and our slope. So we put in, there we go. So we want the tangent line to big F at 0. We need the point at 0. We need the slope at 0. And away we go. Does big L lie above the curve at x equals 1? Now that's a new question. When will a tangent line be above the curve? When the curve is what? Concave down. Matter of fact, in some books, that is the formal definition of concavity, is how it relates to a tangent line. Tangent lines will be above the curve when the curve is concave down. When it's concave up, tangent lines will be below the curve. So when you hear a question about that, it's about concavity. Okay, so this question, so let's repeat it. So when will the tangent line be, or does the tangent line lie above the curve, is like saying, is big F concave down at 1? Well, little f has to be decreasing at 1. Is it? No, little f is increasing at 1. So therefore, big F is concave up. So the tangent line would be below the curve, okay? Is it possible that f of 5 equals 5? Uh-oh, what's that sound like? Speed limit law, isn't it? That's a speed limit law. Is it possible that big F of 5 is 5? Well, what do we know? We know big F of 0 is 10. So if I was going to graph a big F graph, and we don't know where it starts. Well, yeah, we do know where it starts. It starts right there. It starts here at 10. And then what do we know? What does this graph tell us? The slopes of big F. Well, they're above 5, right? These values are between, down here you're at what, 5 or 4 something, and up here you're all the way at like 8. So these slopes are like 8, 7, 6, somewhere in there. So that means if you go over 5, how much you going up? If you go over to 5, how much you got to go up? 30, I mean a bunch, right? And there's no way you're going down, right? There's no way you're doing that. So no way could big F of 5 be 5. Could big F of 5 be 15? Couldn't even be 15, because if you go over 5, to be 15, that means you go up 5. That means your slopes have to be around 1. Well, no way. These y values are the slopes, and they're way too big for that. So it's no in both accounts. Okay, so some good reviews. But that's all chapter 1 right there, right? What was the only thing new about any of those problems? Big F. The fact they were using big F. It's the only thing new. Otherwise, that question could have just as easily been in chapter 1. Everything about it. All right, let's talk about 21. All right, let's go through that. And this, again, the mechanics of this problem. You know, I'm not a huge believer in, you know, do it a certain way and you're locked into a certain way. But there are some times where, you know, it's just to your benefit to think about a problem in a certain way and going through it a certain way and showing certain things, communicating certain things. And I think these types of problems are one of those, these chart kind of problems. So we have G of W equals 7W to the 9th minus 18W to the 7th plus 63. When is this graph increasing? When's it decreasing? When's it have local max and min? That's the question. Okay? Probably on this next quiz, just because of time, we're probably not going to get into the inflection points and concavity. But like I said, we would go through the same business, just do it with the second derivative. Now, our next quiz, so this is going to be over sections 1 through 4. Our next quiz is going to be sections 4 through 7. So we're going to dig into section 4 a little more deeply before our next quiz. Okay, so we're asking, where does G have these things, right? Well, we need what? We need G prime. Because what we did last chapter is we would graph a G prime graph, and we would want to look at it, and we'd want to see where was G prime 0. We'd want to see that it went from positive to negative to positive to negative, because that's what told us all our local max. This was great information about G. If we had it, man, we were in business, because we would just do the chart stuff just like we just did. Well, now we need to get that with an equation. Okay, so we used to get this. Now we want to get it with an equation. So here we go. So we go G prime of W. We got some nice shortcuts. So this is what? 63 W to the 8th minus 126. God, those are fun numbers. But the 63 goes away. That's nice. And now we can factor out a W to the 6th. And that leaves us W squared minus 2 equals 0. Did I do that okay? All right. So that's not a big deal. We can do that without a calculator. All right. You know what I have seen people do here, though? Funniest thing, well, not funny, I guess, but for whatever reason, would you have ever thought of doing that? It's like they subtracted them, right? It's like, yeah, you take out a 6. And I only say this, I have seen people in calculus do it, but I get into this with my Algebra 1B class. I told you we were doing factoring here last week. And so I would say to them, you take out a 63. Well, what does that sound like to them? Not take out, it sounds like take away, right? It sounds like take away, which to them means subtract, right? So I'm always saying take out. I need to say factor, but take out a 63. Oh, it's like subtract a 63. And then what do? They put a 63 there. Now, we wouldn't even use big numbers like that. But if I tell them take a 2 out of 8, they get 6 because they want to subtract it. Okay, but anyway, we know that that's divide. You're dividing it out of there. And so that's a 2, so be careful on that. All right, anyway, so this one here would just be W equals 0, right? Because W, that's the only way that could be 0. And what about this guy here? Plus or minus square root of 2, and you cannot forget the plus or minus. Critical. Okay, plus or minus square root of 2. And this will be fine on a no calculator. There's no problem doing this on a no calculator. Just leave it as square root of 2. Okay? All right. So, now we go. This is the one we did, right? We're doing the right one? Everybody good? Okay. All right. All right. So, now what I say to do with those? Put them on a number line. Do a sign analysis. In other words, we need to figure out these red pieces. We need to figure out the red pieces. Where's the positive and negative go? So we do what I call an F prime number line. And so we're going to have negative root 2 here. We're going to have 0 here. And we're going to have root 2 here. Now, I might put a problem like this on the calculator part. And I might put it on the no calculator part. It doesn't matter. The thing is, here's the deal. What would be different about this problem if this was on the calculator part? Almost nothing. The one thing that might be different is this line right here you might not have on your paper, because if it's on the calculator part, you're allowed to use your calculator to solve an equation. So once you got to here, you could do a solve with that and just solve it. You wouldn't have to factor out and show that work. Okay, so you might not need this line right here, and you might not need these two little pieces here. You would just have those answers there. But you got to write it down. And if you use your calculator to solve this equation has to be on your paper. And then you have to, so get in the habit of, even when you're using your calculator, writing down what it is you're typing in there. If you're doing a slope with slope between 2 points, write that down on your paper, then use your calculator to do it. Get in the habit of doing that, because on the AP test you have to do it. So whether this is a calculator part or the no calculator part, it would look pretty much the same. You still need to have this, because here's the thing. What I want to make sure you don't do is, if this is on the calculator part and it says, where is this graph increasing, where is this graph decreasing, you get to just graph the black graph, see where it's increasing, decreasing, trace, because you can find the maxes and mins, right, when you trace. I want to make sure you understand that is not allowed. You can't just do that, because what you do is you're going to get a point on the quiz. You're going to get a point for setting the derivative equal to 0. You're going to get a point for solving and finding the stationary points. You're going to get a point for having some sort of sign analysis, right? That's how they grade the AP test. So if you just graph that in your calculator and then say, here's the answers, they call that a bald answer, and it's not worth anything. Okay? So that's what I'm talking about. So I might put this on your calculator, on the calculator part, okay, just to balance out the parts maybe, or whatever, but it would pretty much look the same, okay? Now, it would be good if this is no calculator. Clearly, you got to know square root of 2 is about 1.4 or something, so you can put a number that's bigger than that, and this would be 1, and this could be maybe -1. So these would probably be numbers you would try. If it's a calculator part, then it's a little nicer, because you can plug in about anything you want, and it's easier to go back and plug in. That's fine. But, you pick numbers that are pretty nice. Remember what I said the other day, tick marks only on these 3 points. Don't put them with these other little numbers in here. Now, I typically will go back in here and put it there. Okay, because several things. I only care right now about what? Whether G prime is what? Positive or negative. I really don't care what the values are. So when I look at this, what do I know about something to the 6th power? It's always going to be positive. So when I go to plug those numbers in, I'm not even going to plug them into that. Because that part's always going to be positive. So it really only matters what this is going to be. Right? That's all that really matters. So when I put a -2 in, I get 4. 4 take away 2, that's a positive. I put -1 in here, that's going to be 1. 1 take away 2, that's a negative. I put in a 1. 1 squared is 1, take away 2, that's a negative. Put in a 2, that'd be 4, take away 2, that's a positive. Right? So there's my number. Okay? So I'm plugging those into, those red numbers, I'm plugging into G prime, and that's giving me then the same information we had back in chapter 1. And that's great information because it just makes the chart easy to read now. So what do we got? And now this is bad. I don't know that I would take off, but I'm not promising. Look what I did right here. What should that be? This is G prime, not F. Don't call every function F. Okay, I made the mistake right there. It's easy to do. So be careful about that. Okay, but this G prime information. So that tells me G is doing what? Up, down, down, up. Local max, flat spot, because this is a stationary point, remember, this is where the derivative is 0, so it's a flat spot, local min. So we got a max, flat spot, local min, goes back up, okay? And so on that other worksheet I gave you, then, you know, we could maybe start plotting some of these points, right? This packet thing I gave you. The idea when you go through that first page and stuff is that you could then take this number, this is where you could use your calculator to help you a little bit there, but you could take this and plug it into the original, and you could get an actual Y value, and put this and get an actual Y value, and actually plot those points, and then you could get a pretty nice curve with what's going on there. Okay? Anyway, so we can answer the question, where's G increasing? Well, it'd be from negative infinity to negative root 2. And then it would be increasing from root 2 to infinity. It's decreasing from negative root 2 to root 2. We have a local max right there. We have a local min. Oh, for you guys who were gone, if you haven't watched the video, the local max at negative root 2, everybody, if it says justify your answer, which it probably will, for a local max, you've got to say G prime goes or changes positive to negative. So G goes increasing to decreasing. You need to have that when you justify a local max or local min. I'm not always going to write that down when we do these problems. I've shown it to you a couple times now, but on a quiz, if you're doing a local max, local min, it says justify. That's what they're talking about. Okay? Just like you would justify an inflection point. You would say G double prime goes from positive to negative, so therefore G goes from concave up to concave down, and vice versa. Okay? All right. There we go. That's pretty much everything. I mean, you know, as far as the quiz goes, we've pretty much covered about everything that there is, other than just being able to go back and do some practice and stuff like that. There's a couple little things here that I want to go through with you, and then kind of give you some work time on a variety of different things. And again, it feels like there's stuff all over the place, but they're all kind of connected, right? The limits is a little bit of a side trip, you know, because we said the definition of the derivative. So let's talk about this right here. So let's say we had function, so let's do a couple different little things. So let's say we had the function x cubed. Right? And so let's go downhill here. Okay, so what would f prime be? 3x squared. Because our power rule for derivatives says that we bring this power down in front, right? And we do that. Okay. Now, oh, I know. One other thing I was going to mention. I think I mentioned this yesterday. What would happen here? What would you say on one of these tables? And I don't remember if this happened on the worksheet. What if these were negative on this side and this was positive? What would you say? Does not exist, because the car on the left's going to -6 and the car on the right's going to +6. Now, another thing I might say is, and I don't know, I'll probably do this later when we do limits in chapter 4, but if I say, in the direction I say, if the limit does not exist, discuss the one-sided limits. So that's what I would be meaning right there. So if you say does not exist, and then it says discuss the one-sided limits, you'd say, well, as x approaches 3 from the left, it's equals -6. And if x approaches 3 from the right, it equals 6. So that's your discussion. You just write down what's the limit on the left, what's the limit on the right. Okay? So that's one thing. Another thing would be, what if these numbers are getting real big? Like what if, and sometimes they're not real big, depending on, like it might be 10,000 or something. What's going on? If your y value is like 10,000. Might be something like that. Probably a vertical asymptote. Well, what's the limit there? What's the limit right here? The cars meet. So the limit does not exist. Now, probably not going to get into much with infinity, but it's possible. Was there one like that on the worksheet? Did you see one that had some weird numbers? Which one was it? Let's get that worksheet out. Which one?
6.
Number 6.
Negative like
3 million. So it depends on how many zeros you put in. Okay. On the left, and what was the right?
It's like negative.
Both the same.
Yeah.
Okay. So they're both negative infinity. So there you could discuss the one-sided limits. You could just say negative infinity on both sides. Okay. But it still does not exist because they don't meet. Infinity is not a number. So even though they're both going to negative infinity. Now, when we get in chapter 4, we'll talk about how is it okay to just say, if they're both going to negative infinity, is it okay to say negative infinity is the limit? You know, some books will say, yeah, that's okay. I prefer to say does not exist and then put negative infinity. Because technically a limit only exists if it goes to a number, and infinity is not a number. Okay, but that's kind of a technicality, so don't worry about that for this quiz, really. But if you see those big numbers in the table, then yes, you would say that's going to infinity. Okay, and then there was a weird one, another does not exist. Was it number 7 or 9? Was it 9? Wasn't there one that went to like 1/2 and then -1/2? Or that was 10. 10 on one side it was like 0.5 going towards 0.5. The other side it was -0.5. Okay. Oh, I know the one I was thinking of was 7. Wasn't 7 the one that had a different number? Or did it say undefined right at 0? It said undefined? Okay, see, that was the old version of the calculator. See, if you do 1 plus x raised to the 1 over x, when x is 0, if you really get a weird thing, you get 1 to infinity kind of a thing. And the old calculators used to put another number in there, like 2 point. It wasn't even e, it was just, or maybe it was e. Maybe it was e. Right at 0, it put 2.718 or something like that. But then, what was the limit? What was the answer on the 7?
2.7.
Oh, it was 2.71. That's what it was. It was going to 2.718 on both sides, but right at 0, it put a 1. It had a 1 there, not an undefined. Why is that? Well, if you have 1, if the x's are going towards 0, the parentheses are going towards 1, but the fraction, you got 1 over a really small number. Well, that's a really big number. So what you have is a base of almost 1 raised to a really big number. Well, 1 raised to anything is 1, right? So the calculator was putting that as a 1. But again, do we care what happens right at 0 on that table? We don't care. If it's undefined, if it's 1, we don't care what it is. It's what it's approaching, so it didn't matter. But now they fixed that on the calculator, and it does say undefined. That's right. Okay, anyway, those were some issues I thought. Does anybody else have any other questions on the worksheet or anything?
Yeah.
Before going, yeah.
On 8, it like gave me a number for 0.
Yes, and it would, because think about it, but aren't the numbers it's going towards that same number? Now again, we don't care, right? So right at 0, I don't care. But if you think about it, see, 8 is a great example of put in a 0 in there, right? That's the first thing we should always do anyway. What's 0 take away 2? -2, put bars on it. +2, square root of 2. 1.414, that's your answer, isn't it? So this is one of those, so yes, most of the time, remember, when we said, when we do a limit, we take that number, we plug it in. If we get a number out, great, that's probably the answer, okay? If we don't get a number, if we get undefined, that's when we have to investigate. So most of the ones I give you are 0 over 0, something weird going on. But every once in a while, you just get one where there's a number, that's fine. Yep, okay, good. Anything else? Okay, so back to this. So f double prime would be 6x, right? So my question to you is, what's big A? Well, you know for sure it's going to be x to the 4th, right? What do you think? It's going to be 1/4 x to the 4th, right? Let's talk about this a minute. One of the basic concepts you got to understand about derivatives and antiderivatives. Derivatives, we're going to have a bunch of rules. We're going to have a bunch of rules. If it looks like this, do this. If it's x to the 3rd, bring the 3 down in front, drop the 3 to a 2, you got 3x left. So you're going to have rules. Antiderivatives are not quite that way. There are a few rules, but basically an antiderivative is just going backwards. So it's like, it's more of a guess and check. Antiderivative is more of a guess and check. So what we will do when we do an antiderivative is what you could do here is you just say, I think it might be x to the 4th. Well, you know what, let's check it. How would we check it? Do the derivative of it, right? So we'd say, okay, let's do the derivative. Oh, that's 4x cubed. Oh, it's not x cubed, it's 4x cubed. I got this extra 4. Oh, what can I put there to make that 4 go away? 1/4. So I put a 1/4 there, and it makes that go away. So it's kind of a guess and check. So I bring the 4 down in front. Oh, okay, it'll cancel that 1/4, and then I get x to the 3rd. Okay, now, since we're just going backwards, we actually could make an antiderivative rule for this. And it works pretty nice because powers show up so often. If the derivative rule is multiply by the power and decrease the power by 1, let's just reverse that. So multiply by the power, decrease the power by 1. So let's reverse it. Increase the power by 1, and then divide by that new power. Increase the power by 1 and then divide by that new power. You could call that the power rule for antiderivative, okay? But usually when we do an antiderivative, it's more of a guess and check kind of a thing, okay? All right, so that's what we did there. We raised the power up 1 and then we divided by that new power. Now I'd rather write it 1/4 out in front than divide by, but you get the idea. Okay, and that works for anything. So if you have x to the 3/2 and you want to, and there's a 2 here, and you want to do the antiderivative, you leave the 2 alone, you raise that up to a 5/2, and then you divide by 5/2. Well, dividing by 5/2 is the same as multiplying by 2/5. So at the end of the day, you would end up with 4/5 x to the 5/2, right? So if I started with that, we would raise it up 1, which would be 5/2, and we would divide then by 5/2. Invert multiply, you would get that. Now you can check that real easily. Bring that down, that'd be 5/2 times 4/5 would be 20/10, which would be 2, and then drop that by 1. Sure enough, that would give you 2x. Okay? There might be a little bit of that on the quiz. I'm not sure. We'll probably save that for the next go-around, the next quiz, like a little antiderivative. my focus for you will be more going this way, being able to do the power rule for derivatives. I'll tell you more about that on Monday for sure, but I think for this round, it's gonna be just do the derivative. Okay, just do the derivative. But I might give you, what I might do for antiderivatives is probably this, right? Just with that big F notation. So something like 3 through 12, you might get to do that. So that part of antiderivative you should know. Okay, oh, and then the other thing that we talked about. When you do the antiderivative, remember how we said if you have an F prime graph and you want to graph F, right? Where do you start the F graph? What did we say? You don't know, right? Remember that? If you have an F prime graph and we're going to graph the F graph, we don't know where to start, right? It could be anywhere, that whole plus C thing, vertical shift. In other words, when I do the antiderivative of this, technically I should throw on a plus C because I don't know. There might have been some number, that C stands for constant, okay? There might have been some number there. Because when I do the derivative to check it, that constant goes away. So I've got a page here of several examples. So if I start with an F here, and I want to do the big F, all three of those could be the big F. So if I start with 6x, so I raise that power up to a 2 and divide by 2, that would give me 3x squared. But all three of those, if I do the derivative, all three of those give me 6x, right? So whenever we do an antiderivative, there's always this kind of this plus C. But again, not a big thing for our next quiz, so we won't worry about it. Local extremes, we won't get into that. There's another one of those problems. I'm going to let you do that. So these are not problems we need to worry about right now. Okay, that's one you're going to do. Okay, so let's turn to page in your book, because this is the last thing we probably have to talk about. Yeah, page 106. 106. So this is the last thing we probably have to talk about. That is going to be on the quiz. Because this plays right into the idea of limits. So a continuous function. A function is continuous if it doesn't have any holes or breaks or jumps or vertical asymptotes, which is really a break. A vertical asymptote is really a break. Okay? We know what we mean by a hole. A break would be something like this, or it could be a vertical asymptote situation like that. A jump, what I call a jump, would be something like this, where you have a graph with a hole in it, and then it's got another point. That'd be like a piecewise function. This would be kind of in a piecewise function, so it's pretty easy to see where those are at. And then, of course, vertical asymptote again. Vertical asymptote sometimes is just called a break. But, okay, so any graph that has any of those kind of things in it is not continuous. Okay, so continuous basically don't look for it. Now, those are all very non-technical lingo for continuous function. That's fine. But now we're going to give a technical definition of continuous, what it means to be continuous, okay? A function is continuous at x equals a if, and then three things have to happen. Okay, so if any of these three are violated, now I'm writing this a little different than they do in page 106. So page 106, they define what it means to be discontinuous. Okay, so I'm defining what it means to be continuous. So if any of these three are violated, then it's discontinuous, meaning not continuous. Okay, so a function is continuous at x equals a if f of a is defined. Okay, now, you could, if you'll make a little note to yourself, in other words, there must be an output there. There must be an output there. So which one of those up there would violate that? Which one of those up there that I gave you would violate that? The vertical asymptote would violate that. The whole would violate that. Okay? So those two situations would violate that. So if there's a place where the function's not defined, then it's not continuous there. Okay, the second thing that has to happen is the limit as x approaches a of f of x must exist. Now notice the words we use there. We talk about functions exist or do not, limits exist or do not exist. Functions are defined or not defined. So those are kind of two different. Now sometimes we use those interchangeably. We say on the limit's undefined, or we say the function doesn't exist. But typically the function is defined or undefined. The limit exists or doesn't exist. Now which one of those would violate the limit existing? The brakes, right? The vertical asymptote situation or the brake. Right? The cars don't meet. The cars don't meet. Right? The other two, the hole and the jump, the limit exists, right? The cars meet, but there's a problem, right? The cars meet, but there's a problem. The diner's burned down in one case. In the other case, it's moved down and it's burned down and moved to a new spot. Okay. So which one haven't we accounted for yet? We haven't accounted for a jump, right? In other words, here, the limit exists, and the function does have an output, but what's wrong with it? So what would have to happen for it to make it continuous and not have this jump in there? The limit as x approaches a, the limit of f of x as x approaches a must equal f of a. In other words, those two have to be the same. Where the cars are meeting has to be the same as where the output is. And then you can see it would be nice and smooth and you'd never lift your pencil. So that to be violated would be the jump. That's the one that violates that right there. Okay? So all three of these must be in place for a function to be continuous. It has to have an output, has to have a limit, and the limit and the output have to be the same. Okay? So on the quiz, we did that assignment the other day that had that broken piecewise function stuff. So I may give you a graph like that and say, where is this function discontinuous? And then you would list the places, the x values, where it had a problem, right? Any of those places. But then I might also say, why is it discontinuous at those spots? Well, if you got a hole, you would say it's discontinuous because the function's not defined. And I'm going to want you to use this language. I don't want you to say because there's a hole, because there's a break, right? If I ask you why is it discontinuous, I want you to use this language. So if I give you a hole, it's discontinuous because the function's not defined. If I give you a jump, it's discontinuous because the limit doesn't equal the output, that last line. Okay? If there's a break, it's discontinuous because the limit does not exist. Okay, so I want you to understand those three things for continuous.
Can you just condense into one rule though? Because if into rule 3, because if f of a isn't defined, then rule 3 will already look at it.
Because there's no equal, so you could say, is it true? You could say a function is continuous at x equals a if, and you could just say this has to equal this, and this statement doesn't make any sense if this isn't a value and this isn't a value. The only problem with that is you can't use that for your reasoning for all of those, right? In other words, if there's a hole, and you say, well, it doesn't, it's not continuous because the limit doesn't equal the output. Okay, I want more than that. Why doesn't the limit equal the output? There is a limit. The reason the limit doesn't equal the output is because there is no output.
Yeah.
right? So you've got to say that. So you're right, in a sense, that's exactly true, right? I get where you're coming, okay? All right. So, really, for that quiz we have, that's it. I mean, so what are we going to do here? I was going to save the algebra practice limits for after break, because I think it would be good to go back to that. But let me, but I think that wouldn't be a bad thing to practice right now, so let me pull this up. So I'll tell you what I'll do. Let's do this. So on the assignment sheet, so some of you may be thinking, I got the algebra stuff down, I don't need to practice this. So if you look on here, our next homework will be the next group. There's like 3 lines. Okay? So there's the 2, 3, 61, 63 through 67. There's the 2, 4 line. Okay? There's, and then the other side of that worksheet. Okay? So I maybe should talk about the other side of that worksheet, but maybe I'll wait and let you work for a while, then we'll do that. Okay, so I'll talk about the other side of that worksheet, then take about a minute. Okay? I'll do that late, about a half hour from now, towards the end of the period, I'll talk about that. Okay? So you can be working on that book stuff if you want to. Then you also kind of have this packet to be working on, and so I kind of want you to just go through that and ask me questions as you have them. And then again, those are things we can come back to on Monday to talk about, so a lot of different things, and we can come back and talk about all those on Monday. Okay? So let me give you a couple of things, if you're interested here, to do for some of this algebra practice. So let me find a couple of good ones here that would be like ones we might do. I would say this one, if you want to try this right here. Put those together, bow tie those, and bow tie those. I think those would be pretty good ones to do. These other ones are kind of different, not probably the way we would do it. Oh, and right here, just bow tie those. So if you, forget this part right here. Okay, so if you want a little practice on that, you can jot those 3 down. Now, what it's missing is the piece we would have where some stuff would cancel. You're probably not going to get anything to cancel, but that would be another piece I'd probably have all over and then something down here, and then that something would cancel. But the part we have trouble with is more the bow tie thing.
The curve sketching technique, then that's due next month.
Yeah, all of that stuff should kind of, like I said, I'm not going to come in on Monday after Thanksgiving and go around and double check that everything's done, but those are all the things. So those things I just said as far as assignment, the packet, you'd want to have worked on those and spent some time with all that so we can see, okay, what questions do we have on Monday? What do we need to talk about? And then I've got some other things to review as well that we'll go over on Monday. Okay, everybody, just get those copied down so I can move the screen up real quick. Okay, so if you want to do those, if you want to write these down as practice for bow tie, okay, write those down. Oh yeah, okay, can I move this up? All right, and for conjugate, probably any of these would be okay, like maybe that one. That one. And then Some of those right there.
Those answers are kind of off to the side too. I'll leave those up there.
Okay, so if you want to practice on some of those, just for that algebra, and then we'll do some more worksheet. Then again, if you want to come up and see answers, I'll leave this up here. But at least for that part, if you want me to help you with the bow tie, you can do that too. Okay. Okay, sorry, I guess I'm going to leave that up. All right, so on the back of that worksheet, now we've done these problems before, so all I have to do is just remind you, I hope, of what this is saying. Okay, so my contention is that, of course, here's your definition of the derivative, so we can't forget about that. We'll spend some time on Monday looking at that. But that was our definition of the derivative, to find the slope at some point. That's the long way of doing it. That's when we were first introduced to limits, right? And so when we set up a limit like this, okay, then we might be able to do some algebra to it, right? Now this one we're not going to be able to, right? We're not going to be able to do any algebra to this one. We can't FOIL that or whatever, okay? So, but I contend that this limit came from that. Would you not agree? And what it says to do, this is like number 34 and 35 on the homework we had a few days back. What function was I using when I set this limit up? And what is my A value? Right? So what's my A value? No? Right here. Right there. The key to finding the A value is look at the A plus H. Look at the A plus H. Right? When you see the 3 plus H, there, that 3, that was my A value right there. The A plus H. Okay, so A was 3. So what I was finding here was actually F prime of 3 is what I was finding in this problem. Okay, for what function?
X, or
2 to the X function. Now, how did I know that? Well, again, whenever you do one of these problems, I think the most important part to look at is this part right here. Because when we start these problems, what do I always say? I say, what is F of 3 plus H? Oh, it means put 3 plus H in for the X. Put 3 plus H in for the X. So when this problem was set up, the 3 plus H got plugged in where the X was. So that means this function must have been 2 to the X. So what this limit was doing right here was finding the slope at 3 for the function 2 to the X. Now, the rest of the worksheet, I'll be honest, I don't really care about. It says use your calculator to find it. Like, you don't have to go through and write down the tables and everything for that. But we could, right? You could type this in. You could type this into your calculator, right? Except you'd have to take the H's out and put what in? You'd have to put X's in, right? But you could put this in just like we did on the other side of the worksheet. You could put this into your calculator, put in X's instead, and see what it equals, and there you have it. Now remember, I told you yesterday, this is a type of problem I might give you in the quiz. I might say, use the definition of the derivative to set up a limit. Now, that'd be the reverse of this worksheet. I would say, use the definition of the derivative to set up a limit for the function 2 to the X, so you could find F prime of 3. So you would then write out this, right? You would set this up using the definition of the derivative. Then use your calculator to find that answer. So then you would type this in, except take out the H's, put X's in, and then you would find that answer. And you do a table and you look at it, right? And what you'd be finding is the derivative of this, because we don't have a rule for this. We can't use the power rule here when there's an X up there in the power. We can't do that. So we don't know what the derivative of this is. Okay, that's what that worksheet is. So, you got the hang of it? Look at the next one. look at number 2. What's the A value?
3.
3. What's the function we're setting this up with? 2 sine x, right? The 3 plus h was plugged in where the x must have been. That's all I'm getting you to see, kind of in reverse. On the quiz, I'm probably going to ask it the other way, the normal one. Use the definition to set up the limit and then put that in your calculator, right? But I think it helps you to look at it both ways. Okay, so there you go. Lot to do. You got all kinds of stuff you can be working on, which is all stuff that should be helping you for the quiz next week.
Do you want like an answer for that?
So here, that's the part I was saying I don't really care about right now, because we got all this other stuff to do. I certainly don't care if you put your table, right? You just want to type that in as a limit, whatever. To be honest, I don't care. Whatever you think you want to do. If you want a little extra practice doing those tables, right? Putting the table, just typing it in and seeing the table and then write down the answers, fine. You don't have to write down the whole table. On the quiz, you would. You'd write down the table.
It's actually,
Okay.
it's optional for the 5 minutes.
Yeah, I think that's right.